4.6, Green Worksheet number 1. And what do we see? An explosion of graphs. Which graphs? How many functions? Okay, I see 4 graphs, but 3 parent functions represented. What you need to be able to do in this math class, in this unit, and for the rest of this year, is look at a function like this and just know that's a parabola. And its parent function is, okay, the same way that you see someone walking down the hall and you know who they are, right? If you see the V, you should just know it's an absolute value. And when you see this sideways parabola cut in half, it's a square root. It's like, oh, hey, that's Bob, that's Larry, that's Mo. I know them. That's how familiar you should be with these. So the first thing that I want you to do is take A and tell me what the parent function is. Square root of x. B. When you look at B, I'll draw B in green. What's that parent function? Absolute value of x. So let's begin number 1 by writing down what all the parent functions are. Do C and D, pause the video, and see if you were right. So these are the 4 parent functions that you see in red, green, blue, and black. And what we're going to do first is we're going to do the RST, and we're going to figure out if these functions have been reflected, if they've been stretched, and if they've been translated. The first thing I'd like to do is make a little table. Do you have enough room there? The students say yes. Good. Make this little table on your green worksheet, and let's just do yes or no's first. Has the red one been flipped at all? Has the green one? Has the green V been flipped upside down? Yes. The blue one. Is the blue one a V or an upside down V? No flip. And the parabola. It's normally a U. Now it's upside down. So what happens because of that is you need to put a negative in front of them. The 2 that were yes, I can do this because I have erasable ink. I'm going to erase the yes, and I'm going to show you what happens to their equation to make it flip. What about x squared? What makes it flip? The 2 that are no's, I'll just leave the no there. Sound good? Have any of these graphs been stretched at all? Here's how you tell. You take a look at the square root function, and you start at its launch point, also known as its vertex, right? And you determine whether or not it's moving in a normal fashion. Here's what I mean by that. From this point, going to the right, is the square root of over 1, 1. Is the square root of 4, 2. And is the square root of 5, 6, 7, 8, 9 up 3? It looks like it's behaving in a normal fashion. The x and y coordinates are behaving the same way as the parent function. When I go over 1, it's up 1. When I go over 4, it's up 2. And when I go over 9, it's up 3. That's normal because the square root of 1, the square root of 4, and the square root of 9. So my answer to A, has it been stretched? No. Has B been stretched? No. And here's why. It has been flipped, but let's think about the parent function. I'm sorry, B has been stretched. I'm sorry, I was looking at D. I had the back on the D instead of the belly on the B. That's okay. All right, so let's look at B. The answer to B is yes. B has been stretched, and here's why. Normally, whether it's upside down or not, normally the absolute value goes 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. It normally moves in a 1-to-1 fashion. Is it? It's going over 2, down 1, over 2, down 1, over 2, down 1. What has been stretched? The x or the y? The x has been stretched by 2. To stretch the x's by 2, here's what you do. It's still negative because of the flip, and stretched by 2. That's how that dilation occurs. If you doubt me, right now, go to your calculator and graph this. You should see this green graph not shifted. It'll still be at the origin, but it'll be upside down and wider. And we're back. B is the only one that has achieved any type of a stretch. The other two are both no's, and here's why. Look at that other blue V, and look how it's changing. 1, 1, 1, 1, 1, 1, 1, 1. That's normal. That means it hasn't been stretched. And the parabola. I know it's upside down, but as I go from the vertex, right 1, how far does it drop? What's 1 squared? What's 2 squared? 1, 2, 3, 4. Looks normal. What's 3 squared? 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like it's moving in a normal fashion. It has not been dilated. So for both of these, we have no and no. Finally, we need to figure out if anything has been translated, and they all have. Let's find, with a nice little fancy smiley face, where the vertices are. That's fancy for vertexes. All right? Graph A. Normally, it's supposed to go from 0, 0. It doesn't. Where does it begin its little career? Left, down, 4. So it's left 3, down 4. You need to change the red equation to make this radical go left 3, down 4. Left 3, down 4. You're done with number 1A. That's how you make it go left 3, down 4. For B. For B, the smiley face is there. Left 3, up what? 1. Carefully do this one. The negative flips it. The dividing by 2 dilated it. Left 3 would be x plus 3 up top. Up 1 is up 1 at the end. The up and down is controlled after the parent function. C. C looks like it's left 3 up how many? 2. Let's go to blue. Sorry, I didn't do the green one in green. Life goes on. The blue one is left 3 up 2. And the black one? Right 5 up 4. So here's how this works. Negative parentheses squared. Right 5 up 4. Those are the equations for number 1.